Cyclohexane is a ring with 6 carbons, and all of the carbons are sp3 hybridized. So the bond angle should be 109.5, but if you draw a cyclohexane like this on a piece of paper, it looks like it's a planar compound with a bond angle 120, but it's actually not a planar compound and the bond angle is not 120. Because cyclohexane has some flexibility, it can go out of planarity and it can reach the ideal bond angle, which is 109.5 for all the sp3 carbons. Right? So cyclohexane's bond angle is close to 109 and it has more flexibility to go out of this uncomfortable planar geometry to get some relaxed or more comfortable or lower energy non-planar conformation. Right, so non-planar conformation. And it can adapt to many other stable non-planar conformations. By adapting the stable conformations, this molecule can almost avoid all of the angle and torsional strains. There is no angle strain because the bond angle is close to 109.5, and there is no torsional strain because all of the carbon hydrogen sigma bonds are staggered, right, in its most comfortable conformation. So out of the many comfortable conformations, there are a few significant conformations. The one is this. You can see that this is a non-planar conformation. 4 of these carbons, 4 of the 6 carbons, 1, 2, 3, 4, are on a plane, and the remaining 2 are not on the plane. They are projected in and out of the plane, right? So this is non-planar conformation of cyclohexane, and this is called a chair conformation, and it's the most stable conformation for cyclohexane. The next one is called a boat conformation because it looks like a boat. The previous one looks like a chair, and this one looks like a boat. So we call it a boat conformation. Chair and boat. And in the boat, it's again, there are 4 carbons on a plane, and the 2 carbons are not on the plane, right? So these 4 on a plane, and these 2 are not on that plane. Okay. Now, if you draw the Newman projection, we can understand why chair is more stable and boat is less stable. Okay, this is the Newman projection of the chair conformation. If you look through this bond and this bond, right? Because they're both parallel, if you see from this direction, you should probably view through 2 bonds, 2 sigma bonds. Okay. So let's number 1, 2, 3, carbon number 1, 2, and 3. And on the Newman projection, here is the carbon 1, 2, and 3. And carbon 1 and 3 are the front carbons, and there are 2 backside carbons. There are 4 and 6. Carbon 4 and 6 are the backside carbon, 1 and 3 are the front carbon. Carbon 5 is a bridge between the backside carbons, and carbon 2 is a bridge between carbon 1 and 3, the front carbons. Okay, now in this conformation, let's put all the hydrogens on. You can see that the sigma bonds on the carbons are staggered, right? Staggered. They're all staggered, and there is no torsional strain because of that. No torsional strain, right? You can even build a model. It's easy to build a model and look through the sigma bonds to draw the Newman projection. And if you do the same for the boat conformation, this is the Newman projection of the boat conformation, and you can see that these 2 carbons are facing up. In the chair, carbon number 2 and 5, one is facing up, one is facing down. Right? So in the boat conformation, the hydrogens are all eclipsed. And because of that, there is a huge torsional strain, and boat is really unstable. Right? Torsional strain causes a higher energy to that conformation. So that's one reason, torsional strain. The second reason is that these hydrogens, they are projecting towards each other. That will cause some steric hindrance, steric interaction, right? The two hydrogens are competing for a space. So there is additional strain caused by the steric hindrance, and to avoid these steric hindrance, the boat will twist a little bit. So this carbon will go into the plane. This carbon will come out of the plane in order to avoid that this steric hindrance, and which will give a new conformation called a twist boat. Again, there are infinite number of conformations, but here are some significant ones. Right. So this will minimize the steric hindrance. So the bottom line is that cyclohexane is not a planar compound like how we draw on the paper. It should be a non-planar compound. It can be in a chair conformation, a more relaxed state, or in a higher energy boat conformation, right?